Good afternoon, everybody. Thank you very much for coming to this session. My name is Steph. I'm the OHBM chair, and that's where we stop. We're going to start this session with 3 talks that will be here in person. Unfortunately, a couple of our speakers couldn't attend for various reasons. One of them was substituted already. The last speaker, however, couldn't attend very last minute due to visa issues, unfortunately. And so we're going to have a video of a pre-recorded talk. However, Joan Helen Zhu is here in person to answer to any question if you want to make any. We're going to collect, so the speakers are going to have their talks. If we have a little bit of time after every talk, we are going to collect some questions already at that moment. We're going to answer to some questions at that moment. But otherwise, there's going to be a final Q&A of 15 minutes at the end, and so please stay here with us if you want to ask some more questions to our speakers. In asking those questions, you have 2 options. You can use the microphone that is already in the room. It's here in the middle. And otherwise, if you prefer, you can use the app to ask questions, but please remember to write the person that you want to ask that question for, or at the very least, like the general topic, so that we can redirect properly. And if we don't see a name, that means that that's a question for the whole panel. This said, I would like to invite here the first speaker, Nikhil Bhagwat. Nikhil is a PhD candidate at the Institute of Biomaterials and Biomedical Engineering at the University of Toronto. His research...
No, I'm no longer a PhD. I work at McGill. But...
I'm so sorry. Nikhil will correct all of my mistakes. But he's working currently at McGill. Fantastic. His research focuses... I think this part is true, though. His research focuses on algorithm development in computational neuroscience, particularly the application of machine learning techniques to neuroimaging for novel diagnostic and prognostic purposes. Today, Nikhil will share his experience as an early career researcher, discussing challenges in neuroimaging research, fMRI and EEG, and the adoption of open science practices. Nikhil, the floor is yours. Thank you very much.
Thanks, Stefano. My current title actually is Academic Associate, which is still technically ECR or Early Career Researcher, but I work at McGill with Joan Baptiste Pauline in the room right now. I'm going to talk about Breaking Barriers, a practical guide to thriving as an open scientist in neuroimaging research. This is going to be more of a personal story, and it's a story that some of our ECRs have been talking about for a few years now. So this work actually is a joint work between me, Yufeng, who couldn't be here unfortunately, who was also supposed to be speaker here. Disclosures, like I said, I work at the Origami Lab at McGill, and a couple of projects I will talk about today. I'm actively involved in those projects, namely NIPOPI and NeuroBagel projects. So yeah, that's... Cool. So I decided to make this more of a personal story or a case study, if you want to say. So I'll start with my motivation to talk about these topics. We'll go over some of the current landscape of the open science tools and standards and platforms that we have. The dilemmas that early career researchers or junior scientists face in various domains. And then the vision, at least some of us ECRs have for future with open science. Cool. So the question that was posed for the symposium was like, how do we survive in academia as early career researcher and while practicing open science? And I would like to rephrase this bit from an economic theory perspective, and as I usually like to do. So the question I think really on our minds is, if you think of academia as a competitive markets where publications serve as the currency, then open science feels like more of a philanthropic activity for people who are trying to promote and grow open science. And that's something of a problem. So I think 2.5 years ago at some brain hack, so Yufeng, Sebastian, who also couldn't be here today, and I were discussing these topics. We at that time called as a group therapy session, but then soon we realized it could be useful for a lot of ECRs. So we decided to write a paper. And most of the topics I'll talk about today are coming from this paper, which hopefully will be published this week. Cool. So when we were discussing problems in this therapy session, as I call it, the thing that came up, we were just feeling kind of sad on how the open science trajectories were going. And we have all been through this. So when I was a PhD student, as Stefano mentioned earlier, at the University of Toronto, I was in denial. I was in denial because I didn't believe that science could be having wrong. I mean, all these smart people doing such a cool work. Then when I started doing more serious research, I realized it's very hard to replicate results. And again, I actually got angry instead of solving the problems. After that, I realized how actually the academia worked. And it actually became bargaining for data and credit so you can publish more papers. And that actually made me very sad again. So I just couldn't figure out a way how the academia could be changed. And that's when all the brain hack community and open science people gave me hope. And I realized it's basically, we need to think of science as has to be open and replicable, because without replication, it's not really science, it's just your opinion. Cool, so where are these pain points coming from? And as I was migrating from being a student to ECR and hopefully a senior researcher, all of us people were talking that in the beginning, we think of research as we capture data or collect data, we analyze, we publish paper, and everybody's happy. But the reality is that's actually just 10% of your time. So 80 to 90% of time actually goes into what we call data cleaning, data wrangling, just figuring out where everything is. And that takes a lot of time. And this middle part of this research process is actually extremely hard to replicate. And as I turn into even doing research on more data sets or more studies, I realize it's actually it's a loop. It's a recursive process. So you can't just build tools just for one-time use. So you need tools that can actually handle a recursive, repeatable process, and it almost becomes a problem for infrastructure and engineering. Cool. At the same time, open science has been thriving. I mean, there are so many tools. I mean, if you go to OSR or any other talks here, there are so many tools that handle software, research data, and many tools and standards have been around there for over 20 years. But we see there are still some gaps left, and the two primary gaps I'll talk about today is basically there is no standard or tools to actually handle process data or derived data. So if you think of this long process, as I mentioned before, the middle part actually takes a lot of time, but there are no tools to actually share that very time-consuming process. And so these are the gaps we need to fill in open science as we look forward. I think one of the other point was the acquisition sequences as well. At the beginning, I think one of the other speakers will talk about harmonizing those sequences as well. Cool. This is like a big overview of the tools that we kind of did survey during brain hack times. So it's a huge amount of lists, a huge amount of work that has been done. Of course, I won't go through all of them at the same time. What I will do is basically point you to the very last 5 years, where we have basically trying to go from individual tools that handle individual problems, or to think of workflows and end-to-end processes that we could actually share and also reproduce in our research. So last 5 years has been really great in terms of trying to scale our research with the end-to-end tools that can handle that type of things. But there is still a problem with adoption. And one of the reasons there's a problem of adoption of all these fantastic tools is the perceptual gap between open scientists. So we did a survey in our paper where we asked people, how open is your research versus how open is your peers' research? And it turns out everybody thinks they are very open, but nobody else is. So that's kind of like a perceptual gap. Anybody can reproduce my research in weeks, but it takes me a year to reproduce somebody else's work. So that kind of contradiction is also contributing to the problem. Okay, so first we admit the problem, which is it's a complex thing. It's very hard to define, facilitate, incentivize, as many of the other OHBM people will tell you. It's a technical problem, social problem, again, data governance problem, which again, I believe Kim will talk about a bit. And there's also a problem with the career incentives. So the ECRs face dilemmas. In terms of incentives, we have to choose between do we want to do slow, extremely rigorous science, or do we want to do fast science and publish papers? And with the pressures, we usually choose fast science. Same thing with novelty versus reliability. Most publications will promote novel findings over replication papers or reliability of the findings, those type of things. And the funding, of course. The funding usually goes, as I again migrate into ECR position and writing more grants, I realize you have to kind of camouflage infrastructural costs into a cool scientific problem to even have a chance of getting any funding. There's a really cool paper by Russ Poltrock who talks about the cost benefits of doing open and reproducible science. And basically, we have to admit that there's a cost of learning any new tool, and then there's going to be a recurring cost of maintaining those tools. And the point I'm going to make today is that those costs or those investments are worthwhile for long-term benefits. I already mentioned there are other challenges, and other speakers will talk about those as well. Cool. So that brings me to how we think the future of open science and research should be. So in a nutshell, future is just us, or you. If you're an ECR or a trainee, you're going to shape the future of academia, science, open science, whatever you're going to call it. So you have to make choices on how you want to have your future or future of academic research in the next 10 years. What we believe, based on the work we have done over the last few years, that the academic studies, especially in neuroimaging, will have these three things. The data will get larger, and then the data sets will be more multimodal, but they will still remain siloed. You will rarely have a single centralized data set. Then all these people developing new pipelines will continue to release new versions, new variants of pipelines. There are going to be new modalities, new acquisition sequences will require new pipelines, so pipeline multiverse also grows. So what that means is you're going to have to do a lot of research where your computing environment needs to be portable. So you can't just expect one laptop or one computer in your lab that will do all the work until the student graduates, and hopefully it keeps working for the next 5 years. So this is the landscape of near future. Cool. So what happens when you silo data? So in terms of open science, although we really want everybody to share their data completely openly or freely as well, if that's not going to happen, what that makes is that puts the burden of openness onto the workflows. So we encourage people to think just beyond fair data or open code, open source code, to think in terms of fair workflows. So every single step of your research task needs to be now open, findable, interoperable, reusable, and accessible. So if you try to think beyond just data and code, and think in terms of entire process, or research as a service, so to speak. And the case you're making, this is in your self-interest. So it's no longer a philanthropic activity. So if you do this, you will actually have long-term returns that are good for your own personal career growth, as well as just better science. Because if you invest in infrastructure or informatic infrastructure, it will allow you to improve efficiency for large-scale studies, which means more papers, bigger papers, not just small papers. It will solve what we call the N+1 problem, where it could basically, what it means is if you have a new data set or a new population, a new pipeline, or a new site, or new collaborators, anything that comes new, it gets much easier to incorporate into your research. So you build this repeatable, reproducible process that makes this N+1 incremental cost extremely small. And finally, it provides visibility. So we work with a lot of global sites, especially the sites who cannot share their data openly, but by implementing fair workflows or open workflows, they get visibility. So they are discoverable by not just their peers, but globally everywhere. So if you're even still thinking in terms of self-interest, making your research discoverable, even if it's not completely directly accessible, has a huge value to you and your research. Okay, so what do we, in more practical terms, as I said, we want to focus on making your entire workflow fair, which are kind of missing these two components, where we are not still able to share derived data or harmonized metadata, which makes the entire process reusable. And so I'm going to just end with a couple of slides that if you're still very early in your career, in your early researcher, the list we came up with, that it's extremely essential for your research to be reliable and reproducible. I think most open science enthusiasts will know this already. You use bits, Git, Markdown, containers, open portals. This actually goes from, again, data capture to all the way data release type of workflow. And the next list I'm going to show you is, I have to disclose it's extremely biased because this is what we use in our labs and our collaborators' lab. So take this with a grain of salt. There are definitely other tools out there. But again, this came out of our the ECRs we worked with, our personalized case study, and the solutions that worked for us. That's kind of the thing. So I strongly recommend using all of these tools that will really make think of it's an investment into your infrastructure in your lab or in your institute. And all of these are general purpose tools. They are not focused on any of the pipeline that you use or any type of data set you use or any type of study you use. Think of this just general purpose infrastructure tools. And most of these tools address different parts of the FAIR principles, and it's really good. Okay. I'm going to end on more of a slide that is more open-ended. So things I showed you so far, they are meant for something you can do practically yourself as an ECR or as a trainee or even as a scientist. The next things require more of a communal effort or a systemic changes in your institutes and beyond. And this is definitely open for discussion. So if you have questions or thoughts on this, I'm happy to discuss with you after the symposium. The three things we think is critical, based on our surveys and other ECR conversations, is just like there used to be mandate by NIH to release your data. That's just like that. We really think it's important that institutes make their data discoverable. And I want to make clear distinction here that discovery does not mean access. So you're just telling people what data you have. Think of UK Biobank Showcase type of things. What that allows you to get is you know where data are, and then you can figure out how to access it depending on your data governance constraints. But right now, the estimated dark data that we have in neuroimaging is just humongous, and we need to do something about that for sure. The second thing, which probably has been talked about before as well, that we are very heavily dependent on the contribution metric that depends on number of publications, citations, so on and so forth. So something that only revolves around the PDF that you send out to the world. We really think there are more research artifacts than a PDF. So we believe we should come up with new metrics that value data curation, data publication, data processing, software. So all these different research artifacts that make the actual science possible need to be valued more, which are extremely undervalued right now. And finally, this is more of a, you can also say self-interested goal, but I really believe that with growing data, we get more basically statistical power. And with that, you have more responsibility. And to have more responsibility, you need a dedicated personnel to handle neuroinformatics. Infrastructure cannot be maintained by students doing their PhD at the same time. So we really hope institutes build these ladders that go from very early career stage to late stage as part of their job. All right, I'm going to end with the thing. I hope you took some points from this slide, and hope you will jump over all the first 4 stages of grief, and hopefully you will be more pro open science and build this nice open science future together. And I'm going to end with thanking again Yufang, who was the initial submitter of this symposium, and all the other people in my lab, especially all the people who worked on these tools, because there have been 20 years of effort in open science tools, and without them, we wouldn't be able to build the next generation of tools. So really thanking all the people who contributed here. And I think I'm over time, so I'll stop right here.